In this video, we're going to be looking at section 5.5 out of the OpenStax Calculus 2 book, which deals with the alternating series test. The alternating series test is specific to series that alternate. There are series that alternate that yet are not called alternating series. So first, before we get started, we need to make it clear what exactly we mean when we call a series alternating. Look at the definition that's here in the blue box. A series that is called an alternating series is one in which successive terms have opposite signs. That means that if the odd terms are positive, as you see here in the first example, the even terms are negative, or the odd terms are negative, but the even terms are positive. This does not include series of the following form: 1 plus 2 minus 3 plus 4 plus 5 plus 6 minus 7 plus 8 plus 9 plus 10 plus 11 minus 12, even though the signs are alternating and there is a predictable pattern. This is a series, but we do not call it alternating because each successive term does not have an opposite sign from the one in front. If you look to the right, you'll see two examples of alternating series. The first one, -1/2 to the nth power, beginning at n = 1 and going to infinity, is a geometric series where r equals -1. Because the ratio is between -1 and 1, we know that this geometric series must have a finite sum, even though it is an infinite series of terms added together. The second series should look somewhat familiar to you. If you write it in a different form, where the negative is pulled away from the fraction, you will see that this one, in fact, looks a lot like the harmonic series. This is the alternating harmonic series. In contrast to the harmonic series, which diverges, the alternating harmonic series converges. Let's take a look and see if we can show why this must be so. Let's begin by writing out some of the terms for the alternating harmonic series. Again, it's called alternating because the signs alternate in each term, from positive to negative and so forth. It's the harmonic series because it has the form of 1/n, hence the alternating harmonic series. Writing out some of the terms of the series, when n = 1, we know that the power on the -1 would be even, so it will come out positive, which means the first term is 1/1 or 1. The second term will have an odd power on the -1, so it will be negative, and the fraction will be 1/2. Continuing in this fashion, we can see that the alternating harmonic series consists of these terms. Now, if we look at these and we split these into two different parts by splitting the evens from the odds, we can look at their partial sums when we look at them separately. Because these are all added together, it is perfectly fine to separate the evens from the odds and add them together separately. We'll get the same sum as if we had kept them in their normal alternating order. In this case, what I want to start with is the evens, since those are usually easier to write. Let's express this as S sub 2n. 2n is guaranteed that the subscript will be an even number, since multiplying by 2 makes all numbers even. S sub 2n will start with the second term, -1/2. Then it will have the next one, which I can see right now I've got an error in my signs. These should be opposite. This is the issue with having no students in the class to catch my careless mistakes. So the next term would be -1/4 for the even partial sums, and then negative 1/6, negative 1/8, and so on, forever and ever. If we look at the odd terms added together, s sub 2n plus 1 or 2n minus 1, in this case, to get the first one, we should write it as 2n minus 1 so that we can start with the first term. This would give us 1 plus 1/3. Oops, hang on while I get rid of that. Plus 1/3. Looks like my stylus is going wonky again. 1/3. And then plus 1/5, plus 1/7, and so on. If we look at these separately, what's going to happen? Let's start by comparing two partial sums in the even partial sums, s sub 2n. If I were to take s sub 2n, I could write s sub 2n has to be equal to s sub 2n minus 2, which would be the previous even partial sum. Remember that 2n minus 1 would be an odd partial sum because it would have an odd number added in. S sub 2n minus 2 is the previous even partial sum compared to s sub 2n, but it would have to include two additional terms in order to be s sub 2n. The two it would be missing would be plus 1 over 2n minus 1 and, oops, get the 1 on there, and subtracting 1 over 2n. Those added together would give me s sub 2n. The question now is, how did the size of s2n compare to the size of s sub 2n minus 2? Are they equal or not? Is one larger than the other? This comes down to a comparison of the relative sizes of these two terms. We'll start by putting these in the numerator where it's easier to compare how big they are. I know, for example, that if I were to write 2n minus 1, that this would have to be less than 2n. Because I know that 2n minus 1 is less than 2n for all n greater than or equal to 0, then I can write that this must be the case that when I move each of these to the denominator, that 1 over 2n must be less than 1 over 2n minus 1. In order to apply this step, I need to ensure that both 2n and 2n minus 1 are positive values, so I'm not dividing by a negative. In that case, I need to force n to be 1 or greater, but that is the condition on our original series, so I'm fine. Because this shows that 1 over 2n minus 1 is larger than 1 over 2n, that means that when I add these together, I am getting an ultimately positive value. That means that 1 over 2n minus 1 minus 1 over 2n must be greater than 0. And that means that this sum has to be greater than s sub 2n minus 2 by itself. If that's the case, then what does this let me write next? The fact that I've just shown that s sub 2n must be larger than s sub 2n minus 2 shows that the sequence of partial sums for the even terms must be an increasing sequence. That means it's monotone increasing. If I can now show that it's also bounded, then bounded plus monotone means it has to converge. If it converges, then I know that there would be a sum for just the even terms. Let's see if we can show that the sequence of partial sums for the even terms is, in fact, bounded. To do that, I'm going to write out some of the terms that are involved in S sub 2k. To find S sub 2k or S sub 2n, I'm going to write out the terms. 1, the next one coming up is minus a half, plus 1/3, minus 1/4, plus 1/5, and in general, if I keep going in this pattern, I should have the minus 1 over 2k minus 2 or 2n minus 2, depending on which subscript you're using, plus 1 over 2n minus 1 for the next one, minus the last term 1 over 2n. This is what the 2n partial sum would be. Now we can play a trick which involves pairing various terms of this sum together. In order to do that, I'm going to put a plus in front of the minus 1/2 and pair the minus 1/2 and the plus 1/3 together. I'm going to put a plus in front of the next negative term and compare that negative term with the following positive term. That means that I will also be pairing the 1 over 2n minus 2 with the 1 over 2n minus 1 term. In general, you'll notice here that since 2n minus 2 is a smaller denominator, but is negative, this means that it is in fact larger in value for absolute value. Because the larger denominator makes the fraction smaller, and since it's the negative one that has the smaller denominator, that means that each of these values will come up to be some negative number. I can write this for each of the pairs of terms all the way up to the end. The last thing that I have that I can look at then is a minus 1 over 2n, which was also negative, and all of these negative numbers are added to 1. This guarantees that the sum of S sub 2n must be less than 1. That means that it is also bounded above by 1. Since it is strictly monotone increasing and bounded, this tells me that it does converge. Now let's take a look at the odd partial sums. Remember that the odd partial sums are going to be given by adding together the odd terms, starting with 1. The next one, of course, is 1/3, plus 1/5, plus 1/7, and so on, continuing in this fashion. These are the odd terms. We need to see what's happening here for these. If I'm looking at these, how can I write this out using the same method I did last time? Adding together the odd partial sums, I get that S sub 2n minus 1, or in this case, I probably would be easier or better off to go beyond it and try S sub 2n plus 1 and compare it to the size of the previous odd S sub 2n minus 1. When I'm looking at this, the difference between the two is the two additional terms that S sub 2n plus 1 would have, which would be 1 over 2n and 1 over 2n plus 1. Because 1 over 2n is an even term, it is negative, so I have minus 1 over 2n, but the other is odd, so I have plus 1 over 2n plus 1. By playing the same game that I did before and using the inequalities, I can show that 2n plus 1 has to be bigger than 2n. Since I am allowing n to start at 1, I know both of these have to be positive, and then I can divide both sides by each factor, and this would give me that 1 over 2n must be larger than 1 over 2n plus 1. This, of course, then implies that 1 over 2n plus 1 minus 1 over 2n, which is what I have up above, this must be strictly less than 0. Again, this is because the narrow end is pointing to this, and I subtracted the 1 over 2n from each side, leaving this expression less than 0. That means that this is a negative value. That means that when I combine s sub 2n minus 1 with the negative, I must be ending up with something that is going down in value. This shows that s sub 2n minus 1 and s sub 2n plus 1 are decreasing sequences. Now what I need to show is that it is bounded. In order to show that it's bounded, we'll do a similar thing to what we did with the even terms, and we will group them. Let's start by writing out the terms again. The first term is 1. Then we have minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus and so on. Writing out the next terms, I have 1 over 2n minus 1. That would be from a odd term. And the next even would have to be negative 1 over 2n. And then I could include the next one, which would be 1 over 2n plus 1. Which one would this turn out to be? This would have to be s sub 2n plus 1, because the last one I included from the original sequence is 2n plus 1, which matches the subscript here. Looking at these, how could I group these to prove that it is bounded above or below by some value? And which would it need to be, bounded above or bounded below? Previously, we saw that the even sequence was monotone increasing and was bounded above by 1. The odd terms for the partial sums are decreasing. So to make sure that it converges, we need to show it is bounded below. In this case, to make that happen, we will group the first two terms together, the second two terms, the third pair of terms, and so on, grouping each positive with the negative that follows it. In this case, I can see that 1 minus 1/2 would definitely be a positive number. I can also tell that 1/3 minus 1/4 is also a positive number. Because the 3 is smaller in value, its fraction is larger. The larger the denominator, the smaller the fraction's value. That means 1/5 minus 1/6 is also a strictly positive number. And in general, 1 over 2n minus 1 minus 1 over 2n must also be positive. The last term is clearly positive, provided that n is positive. This means I have the sum of strictly positive numbers. There are many numbers that this would be larger than, but the greatest least upper bound would be, or lower bound would be 0. Clearly, all positives added together must be strictly greater than 0. This means that the sequence for 2n plus 1 or 2n minus 1 is both decreasing and bounded below. Since it is both decreasing and bounded below, it is monotonic and bounded, and that means that it must converge. Let's see if we can figure out what is converging to. So far, we've proved that the partial sequence of both the even terms and the partial sequence of the odd terms must converge because they're both monotone and bounded. What we haven't shown is that they converge to the same place. However, we can write the odd terms in this way. S sub 2n plus 1 must be equal to S sub 2n, the previous even partial sum, plus the additional term that s sub 2n plus 1 has, which is 1 over 2n plus 1. Since these two sides are equivalent, let's see if we can find the limit of s sub 2n plus 1 by taking the limit of both sides as n goes to infinity. When we take the limit of both sides as n goes to infinity, on the right we have a sum, which means we can split the sum into the two separate limits. When I split it into the two separate limits, I'm able to look at the second term on the right side, the limit as n goes to infinity of 1 over 2n plus 1. I know that as n goes to infinity, the denominator blows up, which will drive the entire fraction down to 0. This proves that the limit of s sub 2n plus 1 and the limit of s sub 2n are in fact identical. That means that both of these go to the same value. Since both converge and both go to the same value, this means that the sequence of the alternating harmonic series must in fact converge. Using other methods, it can be shown that it actually converges to the natural log of 2, but we're not going to worry about that now. I don't expect you to follow the process to the point that you would be able to reproduce it on a test, but I hope that you can follow the logic of what I've done and that you can understand how we can prove systematically that although the harmonic series diverges, the alternating harmonic series must converge. Let's take a look now at what the alternating series test actually says. The alternating series test, of course, only applies to alternating series. That means that every other term must be positive and every other term must be negative. That means that two successive terms must have different signs. This means you can separate the -1 to the nth power or -1 to the n plus first power from the rest of the formula that produces the sequence, the b sub n, sometimes written as a sub n. The alternating series test is actually quite simple. It says if you can separate the -1 to the power, the alternating form of the series, and if the b sub n, or b sub a sub n, if you're using that instead, is strictly positive after you've stripped away the alternating negative, and the limit of it goes to 0, then it must converge. In other words, if you take an alternating series and you strip off the negative and look at the absolute value of it, if the limit of the sequence goes to 0, then we know it converges. This is similar to the divergence test for strictly positive series, but in this case, it actually does more than just proves divergence. In this case, having the divergence test fail or be inconclusive with an alternating series actually proves it converges. Let's take a look now at the remainder in an alternating series test, and then I will give you a picture to explain what it means. The remainder in an alternating series says, what if I were to use the first n terms of the series to approximate the finite sum of a convergent infinite alternating series? What is the error involved in using that? It turns out that the remainder, the error involved in approximating the infinite sum by using the first n terms only, has to be less than or equal to the value of the next term in the sequence, stripped of the positive or negative. The reason is the remainder must be between s minus s sub n. Let's take a look at a picture and see if I can explain to you why this must be so. We're going to look first at the first sequence we mentioned as being an alternating series which we know is a convergent geometric series. In this case, we have the infinite series from k equals 0 to infinity of -1/2 to the kth power. This is a convergent geometric series because the common ratio -1/2 is strictly between -1 and 1. In fact, we can find the infinite sum, and we will do that in just a moment. Remember that in order for a sequence to possibly have a convergent sum, the sequence itself must go to 0. The first graph you see here is showing that the values of the sequence are going down to 0. You'll notice because it's alternating, we have this above, below, above, below behavior as they narrow down to the value of 0. This just means that the limit as n goes to infinity of a sub n equals 0. That is our original divergence test. That still applies here. Now we look at the sequence of partial sums. If I were to write out this series, this is the series where starting value would be k equals 0, which would give me a 1. The next term would be -1/2 to the first power, which would be -1/2. Then it would be -1/2 squared, or +1/4, -1/2 cubed, or -1/8, and then -1/2 to the fourth, or +1/16. These are the values you see here for the sequence. If we look at the partial sums, the first partial sum, of course, is just the value of the first term, 1. If I add the first two terms together, I get 1/2, which is the value you see here. This is S1, and this one is S2, the sum of the first two. Or if you want to start at 0, you can write it somewhat differently. This is the sum of the first 3, which gives me this value here, the sum of the first 4. Can you see that in a similar fashion to what the sequence did, the sequence of partial sums for the alternating series is also oscillating above and below some particular value? In fact, it is oscillating above what is here as a green dotted line. That green dotted line is the limit of the value of the sequence of partial sums. That's S infinity, or the value of the infinite geometric series. This is the limit as n goes to infinity of S sub n. We know because it is a convergent geometric series that we could take the first term in the series and divide by 1 minus r to find that convergent sum. A first is going to be the one I get when I start at 0 and go to infinity. 0 being the first term means that I take -1/2 to the 0, which means it's 1. The common ratio is -1/2, but that is not the first negative. The first negative is from the formula. That gives me a double negative, which makes it a plus. This gives me 1 over 1 plus 1/2, which is 1 over 3/2, which turns out to be precisely 2/3. This value you see here on the green dotted line is the graph of y equal 2/3. You can tell that the error between any two sets of partial sums has to be less than what it was previously. If we look at this here, you can see that it is this far off of that. This is the amount of error if I use the first 3 terms added together. Notice that this distance is smaller than that distance, and in fact is smaller than that value. That means that the remainder is less than the absolute value of the next term in the sequence. This gives us an easy way of estimating the error of an alternating series. Let's now take a look at a couple of examples and see how to apply the alternating series test. In this particular one, we need to see whether or not we can even use the alternating series test. To use the alternating series test, I have to have a series where the terms in the sequence alternate in sign in each successive term. The presence of the -1 to the k plus 1 does guarantee that I have that alternating behavior. What is the next condition of the alternating series test? The next condition of the alternating series test is basically that the terms of the series have to be non-increasing. If we go back up above to the statement of the alternating series test, you'll notice that right here I have this condition that 0 has to be less than or equal to b sub n plus 1 less than or equal to b sub n. The or equal to means they could stay the same in size, but otherwise they have to be decreasing. If they're increasing, then I cannot use the alternating series test. The second thing that I have to apply the alternating series test is the limit of the sequence has to go to 0. That means there are two conditions in order to apply the alternating series test. Well, I suppose we could say 3. 1, it has to alternate, and it has to alternate in each successive term. So we have to have positive, negative, positive, negative, or negative, positive, negative, positive. Second, it cannot be increasing. That does not mean it has to decrease, but it can't go up in value. We call this non-increasing. We can prove this with a stronger condition of decreasing by using the first derivative test. The third condition in order to apply the alternating series test is that the limit as n goes to infinity of the absolute value of the terms of the sequence must go to 0. This is the same as the divergence test on strictly positive series. With these three conditions, we should be able to apply the alternating series test. On our example, we have proved that it is alternating. We need to prove now that it is not increasing. To prove not increasing, you can do it in a couple of different ways. You could use the difference test, the ratio test, or you could use the first derivative test. I am going to use the first derivative test. When I take the derivative of this, how can I prove that it is in fact not getting bigger in value? If I look at this, what do you think would happen if I were to take the derivative? Again, when we apply the derivative, we are looking only at the absolute value of the terms in the sequence. That means we strip off the alternating behavior, the -1 to the k, or -1 to the k plus 1, or -1 to the k minus 1. Now I'm going to take the derivative of that and see if it is decreasing. This will prove that it is possible to use the alternating series test. I'll write it as f prime since I don't really have another easy way of writing it. On this one, I'm going to use the quotient rule. This would give me the bottom times the derivative of the top. The derivative of 3 to the 2k minus 1 is 3 to the 2k minus 1 times the natural log of the base, 3, times the derivative of 2k minus 1, which is 2. This is straight from Calculus 1, which you may need to brush up on. This is the bottom times the derivative of the top minus the top, 3 to the 2k minus 1, times the derivative of the bottom, 2k, all divided by the denominator squared. The denominator is never going to contribute to the sign of the derivative because it's squared, which means it's strictly non-negative. Now I need to look at the numerator and see what I can figure out in the numerator is also strictly positive and not likely to contribute to the sign. When I look at the numerator, I know that k squared plus 1 will have to be strictly positive for k greater than or equal to 1. I also know that 3 raised to any power, even if it's negative, is also going to be positive, as is the natural log of 3 and is 2. That means the entire first term in the numerator, the whole thing, must be, in fact, strictly positive. The question is, what about the second term? For the second term, I have the negative 3 to the 2k minus 1 times 2k. For k equal to 1 or bigger, 2k is definitely going to be positive. 3 to any power is always positive. Now it comes down to what value of k would make the second term larger than the first one. This is something we need algebra for. Let's come down here and see if we can find out what value of k would make the numerator be negative. I'm going to ignore the denominator since I'm only looking at the numerator. Because the numerator has both a common factor of 2 and the common factor of the 3 to the 2k minus 1, I can factor each of those out of the terms in the numerator. Both of those are strictly positive in all cases, so again, I can ignore them. They are not going to contribute to whether it is a positive or negative numerator or positive or negative derivative. This leaves me with the natural log of 3 from the first term times k squared plus 1 minus, having factored out 3 to the power and the 2, it leaves behind a k. Now I need to know when these are going to be negative. Is this less than 0 for some value of k forever? In order to do this, I can take this and write it as a quadratic equation. The natural log of 3 is just a constant. This would give me the natural log of 3 times k squared minus k plus the natural log of 3. This is a quadratic equation where a is the natural log of 3, b is negative 1, and c is the natural log of 3. I could go through all the algebra to prove it, but the best thing to do would be to take a look and see if the graph will indicate if this is going to be negative in all cases. In fact, if I think about it, I know the natural log of 3 is going to be a strictly positive number because I know that the graph of natural log crosses the x-axis at 1. That means the natural log of 3 has to have some positive value. Since this is positive, this means that this quadratic has to have a shape looking like a parabola going up. That means that at some point it is forever after going to be positive. This is a problem because this indicates that this is in fact increasing, and that means that I cannot use the alternating series test. Let's take a look at another example. Now, in the second example, I have the sum from k equal 1 to infinity of negative 1 to the k plus 1 divided by k factorial. The last problem we looked at was actually quite difficult. This one is much simpler, as are most problems for the alternating series test. Looking at this one, I'm going to strip away the alternating behavior from the rest of it so I can isolate what the a sub n or b sub n is. This gives me negative 1 to the k plus 1, and this is, of course, my alternating behavior. That meets condition 1 to apply the alternating series test. Then it is multiplied by 1 over k factorial. Since k begins at 1, I know that 1 over k factorial, those will be strictly positive. Now I need to prove two things. One, that it is not increasing, and two, that the limit of the sequence goes to 0. The limit of the sequence is easier to prove, so let's attack that one first. The limit as k goes to infinity of 1 over k factorial, which again is only applied to the absolute value of the terms of the sequence, that's clearly going to 0. That meets that condition. The second one is more difficult. The second one is proving that it is not increasing. In this case, I cannot take the derivative to try to see whether I can prove this longer condition because k factorial is not continuous, and I cannot take the derivative of a non-continuous function. In this case, to show non-increasing, I have two choices. I could show that it is non-increasing by showing that 1 over k plus 1 factorial minus 1 over k factorial. To show not increasing, I would need to show that this is less than or equal to 0. This is the difference test. I find the difference test more difficult to apply, so instead I'm going to do what's called the ratio test. I'm going to take the k plus first term and I'm going to divide it by the kth term. In terms of the sequence, what I am writing out is a sub k plus 1 divided by a sub k. If it is not increasing, then this should either be equal to 1 if they're the same in value, or the next term should be larger than the one in front, or smaller rather than the one in front, which means it's actually decreasing, so it's less than 1. In this case, I can easily find that by rewriting what is here in this complex fraction. Let's take the complex fraction and rewrite it. This becomes 1 over k plus 1 times k factorial. Dividing by a fraction is the same as multiplying by the reciprocal, which is k factorial over 1. Writing it in that way, I can cancel the two k factorials, which would leave me with the solution 1 over k plus 1. Provided that the value of k is at least 1, 1 over k plus 1 is definitely less than the value of 1. That proves that it is not increasing. That means that I can apply the alternating series test. And in fact, once you've met the three conditions of the alternating series test, there's nothing else to do except say, thus, the series from k equal 1 to infinity of negative 1 to the k plus 1 divided by k factorial converges by the alternating series test. This is again like the punchline of a joke, and you don't want to leave this part off. This is a serious grading point on the exam and something I'll be looking for. Let's now talk about what it means for absolute convergence and conditional convergence. The next slide talks about what it means for something to converge absolutely. A series A sub n converges absolutely if the absolute value of it converges. That means if I were to take an alternating series test, such as the sum from n equals 0 to infinity of negative 1/2 to the nth power, which is definitely an alternating series, and I were to take the absolute value of the terms of the series, does it still converge? The absolute value of that series would look like this. Absolute value of negative 1/2 to the n would have to be the same as the geometric series n equals 0 to infinity of 1/2 to the n. Since I know that this is also a convergent geometric series, then this converges absolutely. When a series converges absolutely, it means that the alternating series also converges. In other words, we can write in words that absolute convergence implies convergence. We usually use an arrow to show this. We sometimes call it convergence, and sometimes we call it conditional convergence. Conditional convergence is what is typically called when the absolute value diverges, but the alternating converges. So for our purposes, we will probably leave it saying that absolute convergence implies convergence. If the absolute value of the alternating series converges, then the alternating series without the absolute value also converges. This should make sense to you because an absolute value, all the terms will be positive, which means that this sum must be larger in value than the alternating series where every other term is negative. This is using the comparison test. Since this value must be larger than this one, and the larger one converges, then the smaller one must also converge. Conditional convergence is typically what we call it when the absolute value of the series diverges, but the alternating does converge. We have already seen one example of that, and that is the alternating harmonic series. In the alternating harmonic series, we know that the series n equal 1 to infinity of -1 to the n plus 1 of 1 over n, we know that this converges. However, its absolute value, which is the harmonic series, n equal 1 to infinity of 1 over n, this one diverges. Hence, we say that this series, the alternating series, is conditionally convergent. Conditional convergence tells you not only about the convergence of the alternating series, but the non-convergence of the absolute value of the alternating series. The next theorem simply says that if it is absolutely convergent, then the alternating series converges. This is what we were talking about above when we used the comparison test. If the absolute value where all the terms are positive, making it larger than the alternating series, if this one converges, the smaller one must converge. There is another series theorem which your book does not contain, but which you need to know. What happens? Let's see if we can think about it and come up with a theorem that explains what would happen if the alternating series diverges. If the series, and again I'm going to write it as an alternating series to emphasize that, if this diverges, then what could we say about the absolute value of it? What would have to happen in this case? If I take the absolute value of it, then I know that the terms will no longer be alternating in sign, but instead will all be positive. Since all the terms are positive, then this sum must be larger than the alternating series sum. But if the alternating series sum is smaller and it diverges, then by the comparison test, the larger one must also diverge. This is another theorem which your book omits, and it is sometimes written in words like this: divergence of the alternating series implies absolute divergence. If the alternating series diverges, then the absolute value of it, which is larger, must also diverge by the comparison test. Let's take a look at one more example. Let's begin with this problem here. Can we apply the alternating series test? Then can we say that it is conditionally convergent or absolutely convergent, divergent, or absolutely divergent. In this case, when I look at it, I can clearly separate the alternating behavior from the rest of the terms of the sequence. I can do this by pulling the -1 to the n+1 power away from the rest of it and writing the rest as 1 over the square root of n. The first part is clearly the alternating part. Thus, it meets the first condition for successive terms having different signs. Our next one is that it has to be non-increasing. To be non-increasing, this means that it can't be increasing in behavior. I can try to prove a stronger condition by taking the derivative of it. If I write it as f prime, then I can rewrite this as the derivative with respect to n of n to the -1/2 power by rewriting 1 over the square root of n as n to the -1/2. Applying the chain rule, I get -1/2 n to the -3/2. Rewriting this in its radical form, this becomes -1 divided by 2 times the square root of n cubed. Note that in the original series, n begins at value 1. For n greater than or equal to 1, I know that the square root of n cubed will always be positive. 2 is positive, which means that this is always negative. Because it is always negative, I have actually proved using the first derivative test that it is in fact decreasing, which is a stronger condition than what I really needed, which was just that it wasn't increasing. For the third condition, I need to show that the absolute value of the terms of the series is going to 0. This means that I pull off the alternating sign behavior and take the limit of what's left as n goes to infinity. The limit as n goes to infinity of 1 over the square root of n is clearly 0. Thus, by the alternating series test, which yes, you may abbreviate, this proves that that series must converge by the alternating series test, the series from n equal 1 to infinity of -1 to the n+1 over the square root of n converges. Is it absolutely convergent? To decide if it's absolutely convergent, I would need to take the absolute value and strip away the -1 completely. To check for absolute convergence, I can remove that -1 to the n+1. This would give me 1 over the square root of n. However, I know that this is a p-series with p equal to 1/2, and that 1/2 is less than 1, which means that this is a divergent series. Thus, the original series is only conditionally convergent. That means it converges, but its absolute value does not. Let's take a look at another example. In the next example, we have the following series. I have the series k equal 2 to infinity of -1 to the k times natural log of k over k squared. Clearly, -1 to the k provides successive terms with alternating signs. That meets the first condition for the alternating series test. For the second condition, I need to show it is not increasing in value. However, k squared being a polynomial is larger than the natural log of k, and as k increases in value, this will definitely not be increasing. If you want to prove it, we would use probably the first derivative test. Using the first derivative test, I could write that f prime would be, using the quotient rule, the bottom times the derivative of the top, which would be 1 over k, minus the top natural log of k times the derivative of the bottom, which is 2k, all divided by the bottom squared. Again, the denominator will not contribute to the sign because it's squared. Simplifying the numerator, I could write this as k minus 2k times the natural log of k divided by k to the fourth. K to the fourth is strictly non-negative, so whether it's positive or negative is dependent only on the numerator. To take the numerator and separate it out, I will try to figure out when it's positive and when it's negative. I want to know when it is negative, so I write k minus 2k natural log of k. When is this less than 0? I can factor off the common k, and that leaves 1 minus 2 times the natural log of k. And this needs to be less than 0. If I factor out the k, notice that this was originally over k to the fourth, which means I could have reduced it here. If I had reduced it here, I would only have been left with 1 minus 2 natural log of k over k cubed. If I write it that way, though, then I will have to take into account the fact that k cubed can be positive or negative. So you need to keep this in mind when you're doing these. If I'm looking at these, what values will I end up having? I'm going to go ahead and reduce it, even though this gives me an odd power in the denominator, because I know something about k. Namely, I know that provided that k gets beyond 0, k cubed will be positive no matter what. Since my series starts when k is 2, then I know that k cubed is greater than 0 for all the k values greater than or equal to 2. Now I need to decide about the 1 minus 2 natural log of k. When I look at 1 minus 2 natural log of k, I can use algebra to isolate the k. When is 1 minus 2, the natural log of k, going to be less than 0? Moving things to opposite sides, I get 1 less than 2 natural log of k, or 1/2 less than the natural log of k. In this case, if I want to solve this, this is going to happen whenever k is equal to the square root of e. For k equal to the square root of e, which can be written as e to the 1/2, the natural log of e to the 1/2 would give me 1/2. That means that I need my k value to be larger than the square root of e. The square root of e is a number that is approximately 1.65. Provided k is greater than or equal to 2, that will be a negative number, so it should be decreasing. This proves that I can meet the second condition, that it is not increasing. The third condition is I need to show that the absolute value of the terms of the series are going to 0. To prove that, I simply take out the natural log of k divided by k squared and show that the limit is 0. The limit of that is clearly going to 0 by the relative growth theorem. As k goes to infinity, this goes to 0. You can also apply L'Hopital's rule, which is the direct proof that it must be true. This has form infinity over infinity, so L'Hopital's rule applies. When I take the derivative of the numerator, I get 1 over k. The derivative of the denominator is 2k. I can rewrite that limit value as the limit as k goes to infinity of 1 over 2k squared, which is 0. Thus, by the alternating series test, I know that that alternating series must converge. If I want to prove absolute convergence, then I will have to apply it to the natural log of k divided by k squared. To prove that, I would probably use something like the integral test. It would be more appropriate than any of the other tests. Let's take a look at one more type of problem, which is figuring out what the remainder would be. Remember that the remainder in any approximation of an alternating series is less than the value of the absolute value of the next term in the series. Let's look at one of these problems now. Let's consider the series, the sum from k equals 0 to infinity of -1 to the k divided by the quantity 2k plus 1. Again, if you don't like k, you're welcome to use n instead. For this one, let's write out some of the terms of the series so we can get a handle on what the remainder actually means. When k is 0, -1 to the 0 is 1, which means the first term in the series or the sequence is going to be positive. Writing out the terms, I get 1 divided by 1, which means that the first term in the series or the sequence is 1. Now I let k be 1, which is going to give me a negative value, 1 over 3. 2 times 1 is 2, plus 1 is 3. The next term will be positive, and that will give me, now that k is 2, 2 times 2 is 4, plus 1 is 5. This gives me the next term, 1/5. Now k is 3, so I get a -1 power, and then I get 2 times 3 is 6, plus 1 is 7. Looking at the numbers, I can now see and predict that the pattern is 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1 over 11 and continuing in this fashion forever. If I were going to take the first 5 numbers and add them together, I could call this the 5th partial sum or the 4th partial sum, depending on whether you're allowing the partial sum subscript to depend on the first match the subscript of the term, or whether you're allowing the subscript on the partial sums to be how many you're adding together. We're going to stick with the convention that the subscript on the partial sum matches the last term you included, which this means, since I want the sum of the first 5 terms, that this first one is a sub 0, the second is a1, the third is a2, the fourth is a3, and the 5th term is actually a4. So S4 would be the sum of the first 5 since I started with 0. This would be the number 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. If I add those numbers together, what do you get? Using a calculator, I get that the sum of the first 5 terms, or the 4th partial sum, is 263 divided by 315. This is approximately the number 0.835. I want to estimate what is the error between the true infinite sum and this. I will tell you that this is a convergent series. When I look at this one then, what am I getting? I know that there must be some value that represents the difference between the true infinite sum and the sum of just the first 5 terms. This is what we call the remainder. The subscript on the remainder matches the subscript on the partial sum used to produce the approximation. In this case, R sub 4 is the approximation error when we use S sub 4 to approximate this infinite sum. Again, I know it converges by looking at it. I can see the alternating behavior. I know if I took the limit of 1 over 2k plus 1, it would go to 0. And I can also compute that 1 over 2k plus 1 would produce a strictly decreasing sequence by taking the first derivative. Thus, by the alternating series test, I know it converges. Now I'm trying to figure out what is the error from using those 5 terms to approximate it. The error theorem told us that the absolute value of the error has to be less than the next term's absolute value. In other words, the absolute value of the error for R4 has to be less than or equal to the absolute value of the next term in the sequence, which is, in our case, a sub 5. A sub 5 was a negative 1/11th, which means that this sum that I used, 0.835, can be no further off than 1 over 11. The value of 1 divided by 11 is approximately 0.09 repeating. That means that I can't be off by any more than that. If I want a more precise answer, I can use more terms for the approximation by taking a larger partial sum. In this way, I can get the approximation to whatever degree of accuracy I need or desire. Again, the remainder is given by the value of the next term that was not included in that partial sum, in this case, the negative 1 over 11. Let's suppose instead of that I told you I wanted you to find how many terms in the partial sequence you needed to guarantee that the remainder would be less than, say, 10 to the negative 4. In that case, we're solving a slightly different problem, which is find k so that r sub k has to be less than 10 to the negative 4. 10 to the negative 4 can be written as 1 over 10,000. In other words, I have an error that is very, very small. If you write it as a decimal, you'll need 1, 2, 3, 4 places. That gives you 0, 0, 0, 1, 2, 3, 4. Is that correct? Tenths, hundreds, thousands, 10,000s. Yes, that is that value. Clearly, I'm going to need more than the sum of the first 5, or S4, in order to make that happen. In order to figure this out, this means that my R sub k or R sub n has to be less than the first unused term. That would be A sub k plus 1, of course, in absolute values. If I strip off the alternating sign behavior, and I think of the A sub n's as all positive, I could just write this as less than A sub k plus 1. Now I need to come up with a formula that will let me do that. But I know what the formula is. I was given the formula to start. I can let A sub k be 1 over 2k plus 1, ignoring the alternating sign behavior. That means that A sub k has to be given by the formula 1 over 2k plus 1. To compute A sub k plus 1, then, I replace the k with k plus 1. This becomes 1 over 2 times the quantity k plus 1 in parentheses plus 1. I need this to be larger than the remainder. This is going to give me what I need in order to compute how large k needs to be to guarantee that my error is no further off than 1/10,000th of a value. Now I can do the algebra on the denominator, and I can write this as 1 over 2k plus 2 plus 1, or 1 over 2k plus 3. I know that I want this error to be less than 1 over 10,000. So since I want the error to be less than that, I set A sub k plus 1 to be less than that as well. This will guarantee that since A sub k plus 1 is larger than R sub k, and it's also smaller than this, that R sub k will be smaller than 1 over 10,000. Now that I have this inequality here on the right, which I've now ringed in purple box, I can take that and switch sides with the two expressions. I know that 2k plus 3 is positive for k greater than or equal to 0, and I know that 10,000 is positive, so it will not reverse the inequality to switch sides. This implies then that 10,000 must be less than 2k plus 3. Now I want to solve for k to find out what k value guarantees that that occurs. I can subtract the 3 from both sides, and that leaves me with 9,997 on the left and 2k on the right. Dividing by positive 2 gives me 997,000. Did I say that right? 9,997 divided by 2 less than k. Because of this, I can choose, for example, something larger. The 9,997 divided by 2 is actually 4,998.5. However, I want k to be larger than that, so I will choose k to be 4,999. That will guarantee that my error will be less than 1/10,000th of a value. This is the end of the video covering the alternating series test, absolute convergence, conditional convergence, and finding remainders on the alternating series.